Thank you everybody for coming. My name is James Coglan. I work at a company called DXW Digital based in London. We work with organizations in the public sector to help them develop better digital public services. And today I would like to talk to you about breaking changes, how we deal with changes in software over time, release management, and trying to keep our software stable. So for context, this talk comes from my work maintaining, amongst other things, these NPM packages that provide WebSocket-based messaging. Between them, they now get over 20 million downloads a week. They're used in quite a lot of software that you may use day to day. They're used in the Webpack dev server. They're used in Ruby on Rails. So there's quite a lot of things that depend on them for their messaging infrastructure. And so I've been maintaining these since almost 10 years, I think. Yeah, started in 2009. And this talk comes from seeing how how changes in those things affect the ecosystem, what changes impact these libraries, and what effect they have on things that are using them downstream. So a further caveat is that almost all the open source software that you use day to day will say something like this in its license. This talk is not intended to be a complaint about anybody's work. It's more an attempt to reflect on what we can learn and how we can all do things a little bit better. So this is not an attempt to sort of call out or complain about anything in particular. So with that out of the way, let's talk about what we mean by breaking. What does breaking mean? So let's think about this bit of code. So on the top we have this is two versions of a module with a small change made between them. So on the top we have a module called HTTP, and it has a function in it called get, which takes a URL and a callback, and it makes an HTTP request to an endpoint. And when we get a response, we call the callback with a hard-coded with an object with a hard-coded status of 404 as a number. On the bottom we have that same piece of code, but with the number replaced with a string. And we'd like to know if this is a breaking change. If we make this change to our code, will that break anything that's using it? So let's look at some use cases. So if something is calling this this function and comparing the status using the double equals operator, that will continue to work because in JavaScript that operator coerces both of its arguments to strings if either one of them is a string. And so the string 404 is equal to the number 404 under this operator, so that's fine. However, if they're using the triple equals operator, that doesn't do any type conversion, and a string is never equal to a number, so this code will start failing if we make this change. So this is our first signal that whether something is breaking or not depends on how it's being used. Here's another example. This is a module called database with a function called count, which takes the name of a table, and it runs a query to count the number of records in that table. And then when it gets the result, it runs the callback with an object with a count field, which I've hard-coded in this example. Now, something to notice about this is that this code is identical to the example that I've just shown you. All that I've done is changed the names of the names that are in the code. The structure of this program is identical to the previous module. So if we decided that the change that we just saw was a breaking change, we have to give the same answer for this if the notion of breaking change is purely a function of the source code itself. So if we change the number 404 to a string in this example, what happens? So one possible use case is that somebody is counting the records in two tables and subtracting them, for example, to work out the number of unsold tickets for a conference they're running. Now in this case this will be fine because in JavaScript the minus operator converts both of its arguments to numbers before doing anything. So if we're returning strings from this count function, this will still work because the strings, as long as the strings represent numbers, they'll be converted to numbers, the subtraction will go ahead, and everything's fine. However, if we're adding the results together, for example, to count the total number of sessions at a conference, this will no longer work because JavaScript's plus operator performs arithmetic addition if you give it numbers, but it performs concatenation if you give it strings. So rather than the sum of two numbers, we just get their digits appended end to end. So this code will no longer work. And to keep it working, we would have to make a change to it to actually convert the results that we're getting into integers before adding them. So the fact that we've had to make this change means that we consider the change to the database module to be a breaking one. So what's going on here is that we can't talk about whether things are breaking just from the source code itself or just from what their type is, just from knowing that something is a number. That doesn't tell us enough about how it's being used and what aspect of it is important to the programs that are using it. So even something as simple as a number has a set of characteristic traits, different aspects of it that come into play in different situations, and it's which aspects are actually being used that determine whether changing the type of something will be a problem. So we've seen a couple of examples here. A number may be being used for its identity. So an HTTP status code is not a number that you would like to do arithmetic with. It's just a machine-friendly label for a particular outcome. And you'll usually just compare that for equality. You won't do addition and subtraction with it. Or you may be using numbers for doing maths, adding them together and subtracting them and so on. And in that case, their role as mathematical numbers is important rather than just them being a label for something. So we've seen there's quite a lot of complexity in a primitive value like a number. Now let's look at something more complicated. Let's look at objects. What happens when we change the interfaces to objects in our programs? So here's a function called getTalkInfo that takes the ID of a talk and returns some information about that talk. In this case, it returns information about this talk that is happening right now. It has a title, a date, and a presenter, and all of them are strings. So if we add a new field to the return type of this function, that's probably fine. Anything that's calling this function that doesn't know about that field will probably just ignore it. It won't start failing because the object has a new field that it wasn't expecting. However, if we remove a field, that's more likely to cause problems. So for example, something may have been relying on the field that we just removed and will now not work. So for example, if we were calling this and using the title attribute to construct some HTML, the program would not crash, so in that sense it wouldn't be broken, but it's clearly doing the wrong thing. So instead of this producing an error, JavaScript takes the value undefined, which is what details.title resolves to, turns that into a string and concatenates it with everything else. So this is a situation where JavaScript is a bit too lenient. You may hope that something like this would produce an error. It actually doesn't. Your program keeps working, but it does something that you didn't actually want. Likewise, changing the type of a field may pose problems to downstream programs. So if we change the date to a date object rather than a string, if there was some code that was previously relying on being able to split that value to get its component parts, that will no longer work because date objects don't have a split function. So in this case, JavaScript is a little more helpful. It actually throws an exception to tell you your program is not working rather than sort of silently doing the wrong thing. So there's some good rules of thumb with object interfaces. Usually adding new fields is fine. Most things will ignore fields that they don't care about. Removing a field is much more likely to break things because downstream programs will be coupled to those fields, they'll be relying on them. Likewise, changing the types of existing fields has the potential to break existing programs that are relying on those interfaces. But it's not quite as simple as that. So JavaScript being a small language, although it's grown quite a bit in recent years, overloads the small number of concepts that it has with quite a lot of different computational meanings. This is particularly true of the object type in JavaScript, which is used to represent what in other languages would be several distinct concepts. So let's look at a few of those. So one of those concepts is the idea of a map, which you may have heard referred to as a dictionary, an associative array, a hash table, something like that. So this is an open-ended collection of key-value pairs. Usually the keys and the values all have the same type. And you can tell that you're using something as a map if your program doesn't look for specific hard-coded fields in it. It iterates over it, or it looks up the keys dynamically based on data from somewhere else. A record is a data value with a known fixed set of fields, and each of those fields can have a different type. If you're looking up specific fields on an object and expecting them to have certain kinds of values, that means you're using it as a record. The props value that is passed into a React component is a good example of this. You don't tend to just iterate over the props and do the same thing with all of them. You'll look for specific things in them and put those into places in your UI. Then there's the idea of an object as in object-oriented programming, which is a value that combines state and behavior. So it's like a record where some of its fields are functions that interact with the record's other data fields. So the image object that was in the previous example is a good example of this. It has some internal data, like a name, and it has some methods like URL that generates a URL for a particular size of that image. Now, usually adding new fields to an OOP style object is fine. In fact, that's what enables polymorphism. You can pass an object into something that only uses a particular aspect of its interface, and it will ignore all the rest of it. But if you're using an object as a record, adding new fields might actually be dangerous. So an example of this is in Webpack. If you put a field in your Webpack config that Webpack does not recognize, you'll get an error. It won't just ignore that field. And you'll see a similar thing if you pass an unknown command line argument into a program, even though that may internally be represented as a JavaScript object. It may decide to complain if there are any fields there that it doesn't know what to do with. And that's because in this kind of use case, that more often than not indicates a typo, or that somebody was expecting something to be done with that value and it's not actually recognized by the program. And in interactive programs like that, it's more helpful to the user to alert them to that fact than to just sort of silently ignore things that we don't understand. So the way, it's not just the fact that something is a quote-unquote object that tells us what we can do with it. It's the sense in which it's being used. And JavaScript in particular has a little too much ambiguity around that. You also see this if you're inserting records into a database. So if you're trying to save an object into a database and one of its fields doesn't match, like the database doesn't have a column for that field, you probably want that to fail because we can't actually save that entire object. You're going to lose data. And ORMs will typically have some explicit, you have to explicitly say which fields are persisted, either by documenting your database schema or by doing some other sort of configuration. So what we've seen here is that types in programming languages can carry a lot of conceptual complexity. Like one thing can have many different meanings depending on context. So a good example of this was a year or two ago. There was a proposal to add a flatten method to arrays in JavaScript. So this is a proposal to TC39, which is a committee that maintains the design of the JavaScript language and pushes it forward. And there was a proposal to add a flatten method to arrays in the language, and there was pushback against that because that would have broken existing programs that already defined their own implementation for flatten, and this new implementation didn't agree with the old one in terms of what it did. So why is this a problem? Well, firstly, the problem arises because JavaScript programs run in an environment that the author can't control. They go into any number of browsers and devices and operating systems and things like that, and they just have to cope with whatever environment is there, whatever APIs exist in the environment that they end up running in. So any changes made to that environment are potentially very dangerous to us. So changes to built-in classes could change the way that our code runs, because JavaScript lets us add our own methods to built-in classes. If we've added our own array flatten method and then the browser gets its own version that conflicts with ours, we now have a problem. We can't control for that very easily. But there's a more subtle problem with this proposal in particular, which is just the function in question itself is too conceptually complicated. So here's one potential implementation of the array flatten method. We reduce over the array, and for each, so starting with an empty array, we reduce over the array and concat each element onto the result that we're building. And because of how concat works, that will take any arrays that are nested inside the original input and flatten them to one level deep. But that may not be what you want. You may want an infinite amount of, you may want the array to be completely flattened rather than just go to one level. There are also questions about how other sorts of iterable values should be handled. So for example, if the array contains strings, which are iterable, or sets, and the set contains an element that's already present in the original array, or null, there's a huge design space here of you could argue, well, these aren't arrays, so we'll leave them alone, or they're iterable, so we should combine them. And if there's sets present, what does that mean for uniqueness with other parts of the structure? If there are nulls, should they get turned into empty arrays? Should they get ignored? There are a lot of potential arguments you could make for what this function should do. And that means that any two implementations of it are really, really unlikely to have the same behavior, just because there's a very huge design space potential. I think what this indicates is that if you reach for this function in your code, it sort of indicates a deeper design problem. Like if you know that you want to flatten to one level deep, you probably want a method like flatMap that does that specific thing. If you know that your data is arbitrarily nested, then you probably want some sort of recursive procedure that walks over it. You're doing a visitor pattern or an interpreter or something like that. If you don't know which of those you want, you actually have a bigger design problem than just, yes, I want to flatten all my data completely. We also saw this sort of thing show up in the buffer constructor in Node. So in Node, a buffer is just a chunk of memory. It's just some bytes that have been allocated. And this was overloaded with too many responsibilities, and that actually made it dangerous to use. So if you instantiate it with a string, it gives you a buffer containing the UTF-8 representation of that string, the bytes that make it up. Whereas if you instantiate it with a number, it gives you a block of memory of that size. And there was a security vulnerability in some WebSocket libraries where you could, by sending a number as a message in a WebSocket frame, you could get the server to actually turn that into a number and therefore instantiate a block of memory that size and return it to you. And because that memory would be uninitialized, that's a way of getting reading arbitrary blocks of memory off the server. So this ambiguity, this sort of overloading of responsibility in the same function, is actually really dangerous. And we solved that by splitting it into two interfaces. So you can say buffer.from, which is if you want to turn a string into some bytes, or you can say buffer.alloc, which is if you want some memory of a certain size. And that removes the ambiguity. The programmer is now saying exactly what they mean, and there's less scope for the program accidentally doing the wrong thing. So I've talked a lot about return values. When we call functions, we get values back, and we depend on certain elements of those return values. But there are also contracts implied in the arguments that our functions take. So for example, this contains function. The intent of it is to take a list and a value and return how many times that value appears in the list. So one implementation of it is that we'll use a for-of loop, and for each item in that list that is equal to the value that we passed in, we'll increment a counter and then return that counter. Whoops. Yes, that's fine. So this is intended to work with, the author intended this to work with arrays, but because we're using for-of, it actually works with any iterable value. So somebody else takes this function and starts using it with a set. Now for sets, it will only ever return 1 or 0 because the values in a set are unique. But that's sort of useful enough. It tells you whether the value is there or not, which is useful information. So this is all fine, and then the original author of the contains function decides to change its implementation because they only intended it to be used with arrays. So they'll change it to use the array filter method. We're going to filter the list for elements that are equal to the input value, and then get the length of the result. So that continues to work with arrays. That's fine. But if we continue to use it with a set, that no longer works because sets don't have a filter method. So the author's intent here allowed for a bigger set of use cases than the author meant, and when they changed the implementation, some of those use cases got cut off. So even though their intent wasn't for anything to break, the actual usage of their code meant that what they'd done broke some downstream programs. The final thing that we need to look at in terms of breaking changes is side effects. So JavaScript being an imperative language, our programs have side effects on the world, and changing those side effects can cause compatibility concerns. So for example, this function adds a dependency to our package.json by reading the file, parsing it, adding an entry to its dependencies list, and then writing the file back out. So if we add a console.log to that function, is that a breaking change or not? Well, it depends. Is this function embedded in a command line program and we're piping the output of that program into something else that expects a certain output format? It may just be there is some extra logging information that the user can see, or it might be that gets inserted into like a stream of JSON that's being sent into something else and breaks it. If we have an event emitter and we decide to add one more argument to the data with the event that we're emitting, this might be fine. So JavaScript lets you call functions with more arguments than they were expecting, and they'll just be ignored. But somebody might be listening to this event using this syntax that lets them listen to like a variable number of arguments. So if they're expecting to receive, this assumes that everything in states is the same. They're expecting like all the arguments to have the same type. So now our addition of a date value on top of the existing state value we're sending is going to break that code. So what we've seen is that JavaScript is a very permissive language. It allows you to do a lot of things that in other languages might be errors, and it just sort of silently carries on going. When it does give you errors, they're often not very informative. They're not particularly good at telling you which bit of the program is actually at fault. And it's also very hard to tell the compiler what you actually meant because of this overloading between things and the ambiguity that causes. So that's enough complaining about JavaScript being difficult. Let's talk about what we can actually do to cope with these problems. So one common answer to this is semantic versioning. So in the last decade, that's gained a huge amount of traction. And it's the idea that you format version numbers in a particular way as a sequence of 3 digits. And if you release a breaking change, you change the first digit. If you add a new feature that should be backwards compatible, then you change the second digit, and if you're fixing a bug, you change the third digit. And that's fine as far as it goes. It has some conceptual limitations. There are some changes that you can't model in this system. But it's a reasonable way for authors to reveal their intent. But importantly, it's not a hard and fast, like, provable guarantee about the code. All that it's saying is that the author intended that they were just fixing a bug, or that they were adding a backwards compatible new feature. It doesn't guarantee those things. Authors are fallible. Our code may be used in ways that we didn't know about. So a good example of this is that in 2016, a change to the zlib library caused a denial of service error in per message deflate, which is the WebSocket module that does compression. And the reason that happened is that so zlib is a compression library, very, very widely used. It's a C library. It's embedded in lots of different systems. And that accepts some parameters to configure how it does the compression. And the release that they did at the end of 2016 changed it changed that configuration so that some values that were previously legal would now cause errors. They wouldn't be accepted. And those configuration values are part of the WebSocket protocol. So the client and the server can exchange some messages to say, like, how they want zlib to be configured. So now some of the things that are in the WebSocket standard are no longer acceptable to zlib. If you try to use them, your program will crash. So that was at the end of 2016, and that was zlib's first release in 3 years, I think, which gives you some indication of, like, the amount of resources available for maintaining even really, really widely used software. A few months later, in April 2017, Node bundled that. The Node project bundled that release of zlib into a couple of its releases. A few months later, the Fade project, which is what I maintain, detected that issue. While we were preparing a release, we detected this in pre-release testing, and we reported it to the Node project. Miles, who does release management on Node, forwarded that issue to zlib, where I believe it remains open to this day. After a lot of back and forth on what we should do about this problem, we eventually released a new version of per message deflate that papered over the problem. And then the following month, Node released patches that basically pushed the problem down a layer so that we didn't have to worry about it anymore. So this is quite a long process, and it's this sort of gives you an indication of, even when we know what these problems are, it can take a very long time for them to be resolved and for changes to propagate through the system. Like, there's a lot of different software teams and projects interacting over a long time scale. So it's not just a question of, have I broken something or not? It's how long is that going to take to propagate that fix, or how long is its impact going to take to surface? So one approach that we can take for dealing with this is to just try to never break anything, right? That sounds easy enough. And in some situations, this is like a reasonable approach. Like TC39 takes the approach of, like, we will never break the web. We have to never break JavaScript because that would break loads of websites. Last year at JSConf EU, Ryan Dahl, the creator of Node, in a talk where he looked at what he wished he could have changed about Node.js, made this remark: "It's my fault and I'm very sorry. Unfortunately, it's impossible to undo now." There's loads of stuff that he would like to change, but he can't because it will break everything. And in my open source work, this is usually the kind of approach that I try to take. And part of the reason for that is that, as it's something I do in my spare time, I can't guarantee my availability for being able to fix anything that pops up. So it's more valuable for me to try to not break anything because I can't guarantee that I'll be around to fix it if it goes wrong. So I tend not to do compatibility breaking releases. I try to keep everything backwards compatible. In other contexts, it may make more sense to make breaking changes, because you're more easily able to communicate with the people that are affected by those changes. So, as an example of this, my libraries are usually not, the people that are using them are usually not aware that they're using them, because they're a transitive dependency buried inside something that they know that they're using, like Webpack. So if I make a breaking change, there is several intermediaries between me and the end user that would have to make updates before the user sees any benefit or gets their bugs fixed or anything like that. And each of those intermediaries between me and the end user is a cause of delay, like for that bug to be noticed, for somebody to package an update, and yeah, that just adds delay, and it means that people are just less likely to do updates if that's how I did releases. Whereas at my day job, it's a lot easier for me to make whatever changes I'd like, because I'm in direct contact with the other developers on my team. We can all talk about, oh, we need to change this. Oh, we know all the software that is affected. There's no sort of unknown crowd of people outside the organization relying on the software interfaces. So we can make a lot of change as much as we like internally, because we're in direct contact with each other. So you need to figure out where you are on that spectrum in terms of being able to communicate with everybody affected by your decisions, to determine how cautious you need to be about making changes. With my own dependencies on my libraries, I tend to keep them open-ended, just because I don't want to be a blocker. If one of my dependencies releases a security upgrade, I don't want my users to have to wait for me to bump the version number in my library and release that. I just want that to be able to flow without impediment down to the end user. Now, ultimately, all of this comes down to communication, really. It's not a question of, like, can I prove that this code is backwards compatible? It's more about how you're communicating with your users. And there are several ways that we can communicate. So one is in the code itself, like, can we make the code reveal its intention to the best that we can? So, for example, it may be more appropriate to use a set rather than an array, because that tells us more about what the author intended this code to do. Likewise, it might be more appropriate to use a map rather than a plain object, because it tells us, like, specifically, if you remember earlier, object has a few too many meanings. The more specific we can be about what we intended, the less likely it is that people will change our code in ways that would break those assumptions. If we know we're doing string concatenation, it may be more useful to use templates rather than the plus operator, which has some ambiguity. We can't tell if is that addition, is that concatenation, we're not sure. But there are other things that make it more explicit, like using templates or the join function. We can try to avoid using brittle constructions. And by that I mean things that are likely, that make it more likely you'll have to change your program in a breaking way later. So for example, if you have a function that whose parameter list keeps growing over time, the callers to that will usually be sort of hard to understand. They'll have a lot of parameters that you don't know what they're there for. They're not very intention revealing. Whereas if you use an object as the input and you can destructure that, you can provide default values. That means that the callers will name the values that they're passing in, which makes them a bit more intention revealing. And it means they can also just pass in the things they actually want to set and not pass in a big list of stuff that they don't care about. You see this with callbacks a lot as well. So if you have a function, it's a function that we saw at the start of the talk, if you have a function that takes a callback and you want to add a new parameter to it, the callback always has to be the last argument to a function. And so if you want to add a new parameter, you have to do this sort of juggling to keep the existing callers working. So if it's just passed one argument and then a callback, then you need to be able to detect that. Oh, the second argument is a function, right? Well, I'll move everything around, and then I'll do the function as before. Whereas if you use promises, the argument list to the function isn't cluttered with this extra control flow thing. So it's much easier to add a new argument with a default value, and that will keep existing callers working without too much extra pain. You can think about your error design. So we've seen that like JavaScript is not terrifically helpful with its errors. So if you can be a bit more proactive about checking the things that come into your functions and telling the user when they're not what you expected, that can help people write code against your libraries that's more likely to keep working. So for example, the author of the contains function earlier could have put a check in to say, this thing should be an array, and if it's not an array, you'll get a helpful error message. Adding errors to a program later in its life can also be really challenging. So this is an interesting bit of code. This uses a function called pbkdf2, which is used in password generation. And until node 9, this ran fine. What this does is that it takes something like a passphrase and just generates a very large random number from it. This is used if you just need to generate very large random strings. And this worked fine until node 9, when it started failing. And the reason it started failing is that the bytes argument needs to be an integer, but not everything is divisible by 8. So sometimes we're passing in fractional values to this function. That was previously fine. Like Node would just accept that, and that's not really an error. Like all this is doing is asking for a large amount of random data, and if you ask for slightly more random data than you needed and you don't use all of it, that's sort of fine. So it didn't really matter. But then in node 9, we started getting this error. And there's a couple of problems with this. One is that the error is wrong. It's not that the value is out of range, it's that it's not an integer. And the other thing is that it's a program that was previously working is now not working because it's throwing an error with something that it previously accepted. And as we saw earlier, that can cause a denial of service failure. So if you're tempted to add errors to a program after it's out in the wild, consider whether you can continue to keep existing use cases working. Can you maybe just warn the user that they're doing something that may not work? Can you deprecate something for a while before actually changing it? Just let the users sort of transition a bit more gradually over time. You can also like signal things like privacy. So it's quite common for JavaScript users to dig around in objects in the console to figure out what's inside them and try to figure out how to use them. And it's just a useful bit of feedback if you find yourself using like a long chain of things with underscores in them. That's probably a signal that you're accessing something the author didn't intend for you, and that gives you a bit of pushback that you shouldn't expect this code to keep working because you're relying on implementation details. Documentation can be a big help with helping people write stable software against your systems. So a lot of documentation will have prose describing how to use the library, and unless the user is already an expert in the library's problem domain, that may end up giving them more questions than they arrived with, like what is a driver? Is the URL a string or an object? I have a lot of questions about this paragraph. Or can help people get started and give them code that you expect to keep working over time, is if you give them like a fully working example. Like, this is how I intended the library to be used. This is, if I've put this code in my documentation, it means like I'm very confident that this will keep working because this is how you're supposed to use it, and I promise that I will not do anything to make this fail. So if you give them a completely working example, that just gives them something where they can get started, they can then read more about it and actually understand what it does and tinker with it, and there's much less ambiguity about whether the code that they've written is something that the author intended to be workable. And finally, we have testing. So your automated tests can provide a lot of information to users about how to use your software. And testing would be a whole talk in itself. There's one particular thing that I don't see done very commonly, but can be quite strategically helpful. And that's writing tests against your dependencies. So not testing your own code, but if you're relying on particular elements of your dependencies that you're uncertain about, write tests for those, and then you'll get a helpful alert if those assumptions become untrue. So earlier we could have written some tests that check that contains function works with arrays and sets. And then when we change the implementation, we'd have got a test failure saying, actually, this use case doesn't work anymore, and that's why half of your application is broken now. So what have we learned? So compatibility is not just a function of the source code. You can't look at a module in isolation and determine what changes to it would be safe. You have to think about the use cases. You have to look at real-world usage. That context that your code runs in is like the sum of everybody who's using it. And in your job, that may just be the developers that you immediately work with. But if you're doing open source, that is a sort of potentially unknown number of people who are doing all sorts of things with it that you can't know about. And you can influence how people use your code by the way that your code and everything around it communicates with them. And that's how we can hopefully produce more stable systems over time. So that's all I had. If you'd like to learn more, I have a couple of books on, one of them on this subject, one about something else. JavaScript testing recipes will help you a lot with things I've talked about in this talk. Building Git is about all the computer science behind Git. It walks you through building your own client from scratch. Aside from that, that's everything I had for now. Thanks a lot for your attention.